Test. Oh boy. Okay, everything's working. Ugh, I'm sniffly this morning. Hello, everyone. Right. 16 people so far. I just want to double check. Can everyone hear me okay? Excellent. I'm all sniffly this morning. I don't know why. Hopefully it's not a cold. I haven't had a cold since COVID started. It's crazy. All the masking and hand washing, and it's nuts. I haven't had a cold this entire time. So I hope this isn't a cold. But sorry, apologies for the sniffles, but welcome everyone. Hey, it's International Women's Day. Happy International Women's Day. What else is going on in the world? Unfortunately, still the situation in Ukraine. Geez, I've been following the news, and I don't want to make this a whole big rant or anything, but it sure does break my heart. The fact that this is still continuing, and seeing all the people having to leave, yeah, really sucks. Really sucks. So today, today should be a bit of a cool lecture. But before we get into that, what we're going to be doing today is finishing off our lecture on phenomenology, hermeneutics, and technology. And today's where we really get to the fun stuff, where we're going to talk about artificial intelligence. Before that, we'll talk a little bit about hermeneutics. But we'll finish up with some fun discussion on AI. Yeah, Stefan, you're right. I mean, war can last months or years, and I really hope that that's not what we see in this case. But of course, at the exact same time that this is happening, there are conflicts continuing that have been going on for a number of years. There's a war in a civil war in Yemen right now. There is, of course, what seems to be the perennial conflict between Israelis and Palestinians. And it just sucks. I mean, I know that doesn't sound like a very mature take on it, but yeah, like that's how I feel. I don't understand why humans are like this. But maybe when we discuss AI, as Max suggests, we'll have some fun. I should mention that when it comes to the AI discussion, I am going to be riffing a bit. I do have slides, but I'll be riffing a lot. If you usually take notes, good. Otherwise, notes might be a good idea, or you can review the lecture. If I say something that's not in the slides, you can always watch the recording later once it's posted. But anyway, let's share the screen. And let's open up these slides and slideshow. Everyone can see how slow my computer is. That's the next thing I need to purchase. The next big purchase has to be a nice new computer that's good for teaching. Okay. Computer's just catching up with my commands. I would probably later on in this lecture talk about strong versus weak AI. My computer seems especially weak. But before we talk about that, we got to talk a little bit more about hermeneutics. So last time our discussion kind of, it was an interesting one. We talked about, firstly, the sort of analytic continental divide, which I always think this is kind of one of the silliest divides in philosophy. It's one that doesn't really make sense to me. I guess it makes sense in terms of how things unfolded in philosophy, maybe like historically or geographically. But it doesn't make as much sense to me to make a division like this as it does to, say, make a division between, like rationalists or and empiricists or something. And that's because, oh, Tula, come here. Sorry, my dog's distracting me. Come on, lie down. That's because there's actually a lot of agreement between these two traditions, and a lot of nice sort of cross-fertilization that's been happening over the past few years. What? My dog's staring at me like she wants something. Hello, Tula. Can you lay down, and then I'll hang out with you when I finish my lecture. So we're talking about phenomenology and the different approaches between the analytic and continental traditions. Talked a lot about Husserl and Heidegger here, a little bit about Sartre and Merleau-Ponty. And then we got to hermeneutics. Remember, Heidegger's phenomenology is a hermeneutic phenomenology, as opposed to, say, maybe Sartre's, which we could call an existentialist phenomenology. And remember that hermeneutics means interpretation. So hermeneutics as interpretation was initially confined to religious texts, like biblical texts, like doing like biblical exegesis and that kind of thing. Eventually, it became expanded to include other texts from the humanities. Then eventually, by people like Don Ida, to science itself. What does Dusek say? He says, the most lucid and easily understandable application of phenomenology to technology is to be found in the works of the contemporary American philosopher of technology, Don Ida. In his Technology in the Life World and other works, Ida has concentrated on the role of scientific instruments in observation. And he has this really cool argument where technological devices actually mediate our quote unquote scientific perception. So if you remember all the way back to chapters 1 and 2, we talked a little bit about instrumental realism, right? His position is similar to that. He's not arguing that, he's not like an anti-realist. He's not arguing that theoretical entities of science are just that, like electrons are just theoretical entities, not things that we observe. Right, an anti-realist would say, like, well, an electron is real insofar as it can feature in our equations and our models, and we can use it in our theoretical physics to make predictions about the world that we can go out and try and falsify. But there aren't like really little floating electrons out there doing their electronic business. That's what an anti-realist would say. It is not saying that. He's saying that, look, what we see is not, exactly what the world is, or what we're seeing. It's not like, direct contact with reality. Our instruments mediate our perception. Think of a microscope or a telescope, right? Even if we wanted to, we cannot observe microorganisms with the naked eye. And it's really difficult to do astronomy with the naked eye as well. So the objects in those sciences, say in microbiology, microbes, and in astronomy, stars and other celestial phenomena, they're objects of perception that are delivered to us through our scientific instruments, our microscopes and telescopes and so forth. But there's actually two modes of instrument perception, according to Ide. One is where there's a sort of coupling between the scientist, I, and their instrument, which is separated from the object. This is meant to describe the phenomenology of our instruments. And here I'd like you to recall the idea of ready to hand, right? Remember when Heidegger is talking about different modes of being, there's present to hand, which is kind of the traditional way of understanding things. the objects of thought or entities in the world are separate from us, and we can consider them and think about them, and we sort of stand apart from everything. Like I said about the pre-Socratics last time, for example, who believed that we can stand apart from the ordered whole of existence, from the cosmos, and we can use reason and intellect, or logos and nous and things like this, to use the Greek terms, to understand the order of the cosmos. So that's present to hand. But this first mode of instrument perception is more like ready to hand, which was like the hammer example or the eyeglasses example. These things just seem like, when we're using them, they're a part of our body. They don't seem like present to hand unless they break. Like if a lens, like right now, my glasses are ready to hand. They're just on my face. I'm going about my business as if I'm not even wearing glasses, as if I can just see. So my glasses are ready to hand. But if a lens were to suddenly fall out, all of a sudden I'd take them off and go, my glasses are broken. Oh, they're all present to hand now. Oh, shoot. Right? So that would be lame. And that's one way scientists do it. And I know I've been in the lab, and yeah, there's a sense in which a scientist can use his or her tools like a builder uses a hammer, right? And it just seems like an extension of the scientist. But then there's the more of a present to hand sort of mode of instrument perception, where you are separate from the instrument and object, which are sort of coupled. And this describes the sort of hermeneutic side. So this is the phenomenology of our instruments, and this is the interpretive side, the hermeneutic side, where the researcher has to actually stand apart and read the instrument, which is reading the object. This reminds me of in my neuroscience class. In fact, in my PhD studies, I took a neuroscience class, and one of the things we did, which was really fun, was an EEG study. Electroencephalography, where they put all these little electrodes on your scalp and they can detect electrical changes in electrical potential, which are happening in the brain. But when this is going on in real time, of course, the instrument is very sensitive. The participant has to be in a Faraday cage to block any excess electromagnetic radiation. You've got to have all your cell phones turned off, no electronics other than the computer that's running, right? Like a barometer. I don't quite know. Oh, you mean for the right, I see what you're saying. Yeah, like a barometer. Like if you go and check your barometer, if you have one, you are kind of separate from the instrument and object. The instrument and the object, which is, in the case of a barometer, the atmospheric pressure, are sort of coupled together, and you're separate from it. So yeah, that's a good example. Mine's more complicated. Mine is where if you're doing one of these studies, you can see things happening in real time on your screen. You can see like waves. But a lot of this is noise. Like even if I'm wearing an EEG cap and having my so-called brain waves recorded and I blink, the computer picks that up. So then you have to go and do a bunch of statistical analysis. So here, that's also like the second example, I think. But the barometer example is very good. It's a lot simpler than what I was going for. So it's probably a better example. So about this, Dusek says that hermeneutic interpretation of the history of science and science as a cultural phenomenon goes beyond the work of the early hermeneutic thinkers, but is not inconsistent with their approach. However, a more radical expansion of hermeneutics that Ida defends is a hermeneutics of the objects of science, not simply the culture, history, and psychology of scientists. That is, science itself can be seen as having an interpretive dimension to which the early tradition of cultural hermeneutics was blind. So there's a lot that I skipped over there in getting to that quote. And Dusek doesn't quite make this case in the same way that I do. But it's really, on the one hand, you've got the expansion of hermeneutics from religious texts to the humanities to scientific practice to the objects of science itself right here, which is where we're at now. And on the other hand, you have the sort of shrinking from the sort of present to hand, as Heidegger would have called it, understanding, where we are a sort of rational beings who stand apart from the cosmos. And this is very particular to Western philosophy. As mentioned in previous lectures, if you look at, for example, a lot of Eastern philosophy, so say Taoism, or even Shintoism, even Buddhism, we're not separate from the world the way we are in Western philosophy. We're not thought of as separate like that. Same with a lot of Aboriginal religion and folklore, right? Anything that's kind of got a little bit of animism to it, we are very much a part of the living world and not something that stands apart from it with our brains and our reason figuring things out. One of the things that's pushing us further in that direction, I think, is this sort of hermeneutic approach to the philosophy of science. So thinkers like Ida, and of course thinkers like Kuhn, and even Heidegger. This is why Heidegger has had such an influence on the continental side of things, and why some people, I remember in some of my undergraduate classes, why some of my fellow classmates would often ask whether Heidegger had read Eastern philosophy. I don't know if he did or didn't, but there's certainly some similarities there. The direction he goes in after that, as I mentioned last time, though, is quite unfortunate. It's the whole sort of blood and soil thing, which is, yeah, very unfortunate. So that's all I want to say about hermeneutics, because I really want to get to the fun stuff, and the fun stuff is AI. So now we get to Dreyfus and the critique of artificial intelligence. So this is Hubert Dreyfus right here, born in 1929, and he passed away in 2017. He was an American philosopher, but he was a follower of Heidegger's philosophy. And if you decide you want to take a dive into reading some of that stuff, Heidegger, Wittgenstein, but you find it's a little tricky to understand, well, Dreyfus has some of the best explanatory material that you can get. Very good stuff that you can read if you're trying to understand Wittgenstein or Heidegger or Husserl and you can't. Dreyfus's companions are very helpful for that. And his work is kind of unique in that a lot of philosophers, a lot of their work doesn't actually influence how things get done in AI or the cognitive sciences, or in many sciences. I mean, probably maybe the only other person who's had this influence, you know, as a philosopher, at least contemporarily, would be Popper, with falsification, which has influenced scientific practice all over the place, right? That's what we do now. We try and prove our hypotheses incorrect. And that's widespread in the sciences now. Dreyfus's critique of AI has had quite an impact in contemporary artificial intelligence research and in the cognitive sciences more broadly. And these come from his critiques, which he's written more than this. But perhaps most famously, What Computers Can't Do, which was a 1972 book, and the follow-up, What Computers Still Can't Do. This is sort of his claim to fame. So what is he criticizing? He's criticizing what is sometimes called symbolic, sometimes it's called classical AI, or sometimes GoFi, which I think is the silliest abbreviation ever. GoFi stands for good old-fashioned AI. And what does he claim? Well, as Dusek writes, Dreyfus claimed that although the symbolic processing approach is appropriate for formal logic and mathematics, for areas such as understanding natural language, classical AI does not appropriately model perception and everyday reasoning. So to appreciate this, we need to try and discuss classical AI for a bit. Before I do that, let's make a little distinction that is not in the slides. This is one of those things you might want to write down. So everybody's heard of AI, artificial intelligence. I'm sure everyone in this class has heard of that. You are using it now. You may not think of something like Zoom as artificial intelligence, but there's an argument to be made that it could be considered AI. I'll put this question out. Let's just start riffing here, okay? Who thinks that we actually have AI now? Artificial intelligence, like proper AI. Do we have that? Have we invented it? Zach says yes. Jonah says yes. Sean, yes. Max, yes. All right. I'm surprised we're not getting any no's yet. Excellent, Tess. That's what I was looking for. Well, I'm not sure if I would say strong. I don't know if we have strong. Abby says no. Thomas says it depends. Cameron says weak. Yeah, weak AI we have for sure. So some of you suggested, yeah, there are some distinctions we can make here. As we'll see in a moment, yeah, say no. Really, the answer is yes and no. It depends what we mean, right? As Tess and Cameron are kind of hinting at, there's a few distinctions that we can make, right? We want to have strong AI. This is what Newell and Simon called general intelligent action, or artificial general intelligence. Yeah, Elia, I'm not sure. I might have to agree with Max. I'm not sure. We'll maybe be able to answer this question after we have this lecture, whether we have the technology to do it, but we just haven't yet. So yeah, as a few of you said, we can make a distinction. Like Newell and Simon say, we'll get to them on the next couple slides. They want artificial general intelligence, an AI that could do the same kinds of things that a human could do. This is artificial general intelligence, or strong AI. But there's weak AI as well. Weak AI functions within a limited domain. Maybe it only does one thing, like a chess playing program. A good chess playing program could beat me, could beat chess players that are a hell of a lot better than me. I'm not very good at chess. A good chess program can beat the best grandmasters, but it can only play chess. It can't do anything else. You know, so that's weak AI. Excuse me. So we want strong AI. Strong AI is probably the kind of thing you're thinking of if you're familiar with science fiction, right? Strong AI would be like the robots of science fiction, maybe some robots from Star Wars. You know, you got like R2-D2. He's an astromech droid. He has to help fly a spaceship. But he's also like this Swiss Army knife in space, where he has all these tools where he can open a door or fix something or whatever, right? Or Commander Data from Star Trek, an android who surpasses humans in many ways. He doesn't have emotions, though. But he's stronger, faster, smarter, strong AI, right? So that's a distinction that we can make right off the bat. And one thing that kind of comes along with that is this observation that I think comes from Russell Norvig. And that is that when we develop some kind of AI, it's usually hailed as this amazing breakthrough. Oh, it's AI. Wow. But as soon as the technology becomes ubiquitous, it just starts to seem like weak AI, just a tool that we use. It doesn't seem all that special anymore. You know, think of facial recognition. That's something they used to show in movies. You know, like some James Bond, some Mission Impossible type stuff. And you know, back in the day before the technology was available, it seemed super spiffy and impressive, especially if you're imagining some kind of James Bond like scenario where he's sneaking around and doing the face scan or something. Of course, we have this now. We have this all in our phones. Well, really, it's more accurate to say it's done through our phones. A lot of the computing is actually done on the cloud. But yeah, facial recognition, where you have, if you're on TikTok or something and there's a filter that makes you look like something, facial recognition. So it seems really spiffy before the technology is widespread and if you feature it in some kind of cool sci-fi sort of scenario, but it actually seems quite mundane in everyday life, right? Or the internet itself is a great example. There's a really cool clip you can find of thinkers. You know, you can find these old thinkers like Isaac Asimov and Arthur C. Clarke. You can find these on YouTube, talking about what the internet will be. Like one day you'll be able to access the world's knowledge from your home, from a thing on your desk, or from a device in your pocket. Sounded pretty amazing. But you know, what do we do with the internet now? I mean, the internet is mostly porn. And what else? Well, lots of memes, a lot of misinformation, social media. What are we really doing with it? Are we using the internet to its full potential? I don't think Isaac Asimov or Arthur C. Clarke would say that we are. So anyway, that's just one example how when some AI is new, it can be very impressive. But after a while, it doesn't even seem like AI anymore. It just seems like some kind of tool. The internet's not AI, but it is, you know, this is just meant to be a sort of example of the same kind of thing that can happen with these sorts of technologies. So what about classical AI? Well, classical AI probably falls within that weak AI. Well, really, everything falls within the weak AI category. But what is classical AI? If I can switch my slide. Let's get myself out of the way here. So classical AI is sometimes called symbolic AI. And really a lot of this is due to Alan Turing, who I don't talk about in this slide, but I do talk about quite a lot in my Minds and Machines class. I don't have the latest iteration of this class on YouTube, but I do have the first iteration of that class on YouTube. So if anyone wants to go and learn more about Alan Turing, they can check those lectures out. But Alan Turing is sort of like the godfather of AI and computer science. He wasn't the first person to invent the computer. Computers are actually a lot older than people think. There are ancient computers, analog computers, but ancient computers nonetheless, like the Antikythera machine. Yeah, exactly, Ian, about the internet. That's exactly right, right? Yeah, right here, that's more computing power than what got the Apollo astronauts to the moon. But what are you using it for? I mean, so yeah, that's a good way of putting it. So Alan Turing was not the first person to invent the computer. He didn't invent the computer. There are old analog computers of various kinds, like the Antikythera machine, Antikythera mechanism. We mentioned this before. Somebody brought up the fact that for years, it didn't function as technology because it was just sitting in a museum and we didn't know what it was. But it turns out it was actually used for navigating, for reckoning your position in the sea. So computers of certain kind have been around for a while. The first digital computer was invented by Charles Babbage. Who, Max Turing? Well, this is different. This is what you're talking about. The bomb. The bomb was the computer that Turing built to crack the Enigma code. But we'll get to that. This work I'm talking about now theoretically happened a lot earlier than that. So anyway, Babbage invents the first digital computer. He was the Lucasian professor of mathematics, the same chair held at one time by Isaac Newton, and which would be held in future by Stephen Hawking. So he invents a digital computer that works on punch cards. And one of the first computer programmers was his friend, the lady Ada Lovelace. So Ada Lovelace, Lady Lovelace, was one of the first computer programmers. So yeah, International Women's Day, and we're talking about the first computer programmer who was a woman. Awesome, awesome, freaking awesome. So yeah, Turing didn't invent this, but he formalized it. Now, what does that mean? Okay, so Turing used this as idea of the Turing machine. We call the Turing machine the Turing machine. We call it that in his honor. But what it is it's not actually a machine. It's like an idealized or imaginary mathematical version of a digital computer. What makes something digital, by the way? Does anybody know? Like, you hear about the difference between digital and analog, but what does that mean? Well, I'll tell you. It's all to do with representation. Oh, there's answers in the chat. So ones and zeros, yeah, digital information is expressed in ones and zeros. A screen, no. Not the capacity to do multiple things. Information is discrete. Yes, this and the ones and zeros, right? It's all to do with how your information is represented, because that's what we're doing with any computer. We have to represent information. We have to have representations that the computer can operate on, right? It has inputs, represents something, changes those, computes, and then bloop, outputs, which are also representations. In an analog computer, or indeed any kind of analog representation, the representation is continuous. Continuous, like, think of, for example, a vinyl record. Maybe your parents or grandparents have some of those kicking around. Or maybe you're into vinyl, I don't know, but you look closely at a vinyl record and it's all just like continuous grooves, and the needle goes in, and that's what makes the sound. It's a continuous representation. But as Thomas says here, in a digital representation, the information is discrete. It's ones and zeros, as Stefan says. Zero, by the way, is used to represent false. These are all used to represent truth values. Zero represents false, one represents true. And we can use this to represent all kinds of stuff, all kinds of logical relations, which is how we make computer programs. So a digital computer is a discrete state machine. It's digital, 1, 0. It can only be in one state at a time, right? Even your computer or your cell phone, when it's processing, it's only doing one thing at a time. It's doing it very fast, but it's doing it one thing at a time. So Alan Turing's Turing machine is like this. It's a mathematical sort of model, an idealized computer, and it has a tape, an infinitely long tape where we can type symbols. So we can represent information with the symbols on our tape. The tape can be moved to the right or the left by the machine head. The machine can head like write symbols, delete symbols. It can do all kinds of things. There's a screen so that the operator can see what's going on. And there's a machine table, which contains all of the instructions for the machine, records all of the possible states of the machine. In other words, what we would call the computer program today. So what does Stefan say? In the real world, computers, they're defined distinctly from their use of random access memory. Yeah, like no computer has infinite memory or infinite storage now, but Turing imagines that his does. That's why it has an infinitely long tape, right? And Turing also was writing before we made a distinction between storage and memory. For Turing, it's just memory or storage. He uses them interchangeably, but they refer to the same thing. This is before computers had RAM, right? So, yeah. So Turing has this machine that can compute. It's imaginary. He never made one. It's just imaginary. But the really cool thing is that because it's a digital machine, you know, everything can be represented in terms of numbers. The symbols on the tape, the states of the machine can all be represented in terms of numbers. And this actually allowed Turing to formulate mathematical proofs about the properties of these machines. And he was able to prove, among other things, that there exists a special kind of Turing machine called a universal Turing machine. And this universal Turing machine could run any specialized Turing machine. And this is the theoretical forerunner of the modern digital computer. So this basically, if the Church Turing thesis is correct, which is basically this, what I'm saying now, the Church Turing thesis, named after Turing, as well as his doctoral supervisor, Alonzo Church from Princeton. That means that this is a universal Turing machine. My computer is a universal Turing machine. It can run any specialized Turing machine, i.e., any program that is computable. Anything that's computable. Now, there's a lot I'm glossing over here. Okay, again, Minds and Machines. If you want to know more, check that out. It's all about AI, the human mind. What is a mind, right? It's my favorite class to teach. So if you want, check it out. But so Alan Turing comes up with this idea of the Turing machine. It's a discrete state machine, a digital computer, can be in one state at a time. Yeah, great. And Newell and Simon, who are over here, Alan Newell and Herbert Simon, they're playing some chess. They would pick up a lot of Turing's work. Turing passed away in the early 1950s. It's possible that this was because he committed suicide. Then again, it's possible that it was an accident. The case for suicide comes from the fact that Turing had been convicted of gross indecency, right? At the time in Great Britain, it was illegal to be gay, and Alan Turing was gay. And he was convicted of gross indecency. Yes, that's right, Max. That was the punishment. So, and again, all of this is in my Alan Turing video. Maybe I'll link it in somewhere. But basically, Turing threw a spat with an ex-lover, which resulted in a burglary. It was made known that Turing was a gay man, and he was given the choice between prison and this sort of estrogen therapy. Actually, Sean, no, that's not true. This is purely from the movie, The Imitation Game. This is an invention of that movie. Yeah. Yeah, there was a lot wrong with that movie, okay? That movie was not a perfect movie. I mean, it was an okay movie, but it took some liberties with Turing. You know, like in the movie, he's like got like super Asperger's or something. It's crazy. He was not like that in real life. And I'm not saying that he may or may not have been on the spectrum or whatever, but he was not that awkward. He actually had quite a well-developed social life. Yeah. Oh boy, a separate piece. Yeah, I haven't. Geez, that takes me back. Okay, so Turing is convicted of gross indecency, and he has the choice. He can have prison time. I actually don't know. I haven't seen it, but I should. Maybe I'll watch it and I'll talk about it. Anyway, so prison or this artificial estrogen hormonal therapy, which Turing took. And the intent here was chemical castration. Yeah, it changed him. It did change him. I mean, of course, you take hormones, it will change your, you know, whether it's something awful like this or You know, if someone's transitioning and taking hormones, it changes the body and the mood and the mind. Athletes who take like hormones as steroids, of course, it changes things. And this changed Turing. His mood changed. He grew breasts. He was very isolated. He started to change some of the work he was doing. He moved from computer science to mathematical biology. So there's some debate about whether he killed himself as a result of all of these events, whether he was driven to suicide, or whether it was an accident, accidental cyanide poisoning. We may never know. But one thing is certain: without Turing, we would not have these wonderful machines. And also his work in World War II, which Max mentioned. He worked as a cryptographer. That's what the imitation game was about. Another thing wrong with the imitation game is it makes it look like Turing built that entire machine by himself. He didn't. He had an entire team that he worked well with together. And a lot of it was based on work of Polish cryptographers, as Max said. When the Soviets and the Nazis invaded Poland, a lot of Polish academics went to the United Kingdom, and they brought their work with them. And they had already been working on trying to crack the Enigma code. So Turing used that as a starting point and built a new computer called the bomb, which could work out the configurations of the Enigma machine and allow ciphers to be read, right? Okay, enough about Turing. I mean, I could go on about Turing for days. He's kind of my hero, I guess. I mean, he's one of, I like Alan Turing. He's a boss. So what is a classical AI, really? What is symbolic AI, really? Well, that's what gets us to Newell and Simon, Alan Newell and Herbert Simon, who you saw playing chess there on the previous slide. They came up with something called the physical symbol system hypothesis. This is a very strong claim. Admit. Oh, I've actually left out the physical symbol system hypothesis. Oh my goodness, how could I have done that? I left it out. Or maybe it's on the next slide. Nope. Well, that's okay, because luckily I know the physical symbol system hypothesis. The physical symbol system hypothesis says that a physical symbol system has the necessary and sufficient means for general intelligent action. That's a very strong claim. So the physical symbol systems, digital computers that run on physical symbols and algorithms, have the necessary and sufficient means for general intelligent action. The necessity claim is basically that nothing can be intelligent, nothing is capable of general intelligent action unless it is a physical symbol system. That's a strong claim, because it means that I must be a physical symbol system. And I might be. If Jerry Fodor is right, and there is a language of thought, this is not a natural language like English or French. This is a language of thought, a symbolic language. The symbols that are, I guess, implemented by my neuronal firing patterns or something like that, right? So nothing is capable of intelligent action unless it's a physical symbol system. You can see that's a very strong claim. The sufficiency claim, no obstacle to developing such a system, but it's got to be a physical symbol system. If you have a physical symbol system, you have what you need to have general intelligent action. So these are strong claims. So if we want artificial general intelligence or strong AI that would be on a par with a human being, which is what Turing imagines in some of his earlier work, or his later work rather, the Turing test. No doubt you've heard of the Turing test, a sort of test of whether a machine can think. Really, it's a very Cartesian, the Turing test. How do you tell if something is thinking and has a mind? Well, it talks to you. You can talk to it. You can converse. You can express your thoughts, express your reason via language. It's very Cartesian, right? Turing thought that if a computer could do that, we'd have to just say it was intelligent. It's an operationalist test. This is more of a conceptual sort of definition of intelligence. But what is a physical symbol system? Well, physical symbol systems are a kind of artificial intelligence that's implemented in discrete state machines, in digital computers. Four following characterizations, or the four ways we characterize physical symbol systems, are as follows. We have our symbols, which are physical patterns. So symbols are physical patterns. That's number one. What does that mean? Well, think of the zeros and ones in a digital computer, right? Are there really zeros and ones in the computer? If we open the computer up and look close enough, are we going to see some zeros and ones in there? Really? Are we? No, of course not, right? Yes, Kripa, that's exactly right. No, we're not going to see them. High and low log. Well, we'll get to that. But yeah, if we open a computer up, we're not going to see zeros and ones. But what we will see are like things like circuits and switches. Yeah, we get electrons, transistors. We get a bunch of electrical stuff, right? And this goes all the way back to the work of Claude Shannon, who, like Turing, worked as a cryptographer during the Second World War. He worked for the Americans, not the Brits, but they were on the same side. And he also published his, I believe his doctoral thesis was about using electrical circuits to represent information like logical relationships. Claude Shannon is the father of information theory. He gave us like the bit. You've heard of bits of information, binary digits, bits. That's from Claude Shannon. So we have these symbols. So like I said, if you look into a computer, you're not going to see zeros and ones, but you will see like switches, transistors, circuits. So let's say we got switches. Now, they aren't really zeros and ones, but they're representing those truth values by being off or on, right? If I have a switch that's off, that represents 0, which also represents the value false. If I have something that's on, then that represents true, or the number 1, right? So those are our symbols, and this is like way low down stuff. This is like the rudimentary machine code, right? Zeros and ones. Symbols are physical patterns, but we can represent more and more complicated logical relationships with just this. Like we can build AND gates and OR gates, and then we can use those logic gates to build more complicated ones. Eventually, we can build programming languages and just write programs in programming language, like Python or something like that. But at the bottom, it's all physical patterns. The circuits or switches in a computer being on and off, or the symbols on the tape of a Turing machine. Those are physical patterns. So symbols are physical patterns. Yeah, exactly. So the AND function and the exclusive OR function, as Zach says, if you put them together, you could make an adding machine. And if you have an adding machine, then what you have is basically a specialized Turing machine, right? And your universal Turing machine, your computer, can run this, right? And you can make these gates in, you don't even have to know like a programming language. You can make these logic gates in Excel, or you can, if you're, oh yeah, you could use dominoes. There's also a really cool toy. I want one so bad. It's called the Turing Tumble, where it's like you're dropping marbles and they're going all every which way, and it uses, you set it up so that it represents the way information flows through a computer. I really want one. It looks really cool. It would be great for a class like this, just for demonstration purposes, or just to, if you're bored, you play with it. Yeah, I'm a bit of a nerd like that, but okay. So we got number 1, symbols. Symbols are physical patterns, zeros and ones, circuits that are off or on. Then characteristic number 2, symbols can be combined to form complex symbol structures. Sometimes we call these expressions, right? The analogy I like to draw here is between letters and words and sentences. So our symbols are our letters. But we can put those symbols together. The letters are physical patterns, right? But we can put them together to form words and put the words together to form sentences. And these are expressions. These are sentences in our symbolic programming languages, right? And the third one, the physical symbol system contains processes for manipulating complex symbol structures. These are rules or algorithms. This is really what Turing did that was like so important when he's talking about Turing machines. Turing wanted to sort of formalize computation, you know, show us what computation is in a formal system, a system that has, you know, axioms and assumptions, and then you can formulate sentences and derive proofs about them, like math or logic. You know, these are formal systems. Turing wanted to do this with computation. And he did this by borrowing the idea of the algorithm. The algorithm is actually a very old idea. It comes from a guy called Al-Khwarizmi. I believe he was a 6th century Egyptian scientist. He comes up with these step-by-step mechanical procedures. Come here, Toots. Come on down. Sort of step-by-step mechanical procedures for solving problems in a definite and circumscribed way. And Turing borrows this notion. This is how he understands the rules in computing, and also how Newell and Simon understand it. So there are rules that tell us how you can legitimately manipulate these expressions, these sentences, if you like. So we have our symbols, our letters, and we can use those symbols to make statements, you know, tell the computer what to do, write the program. And it's got rules. We need rules, which, number 4, can themselves be represented by symbols and symbol structures. So all these 4 things, if you have these 4 things, you have a physical symbol system. And this is indeed the way that most computers now work. You could even make an argument that all computers, except maybe quantum computers, work this way. There is another approach, which we'll talk about at the end, neural networks, right? Parallel distributed processing, connectionism, neural networks. But here's the thing. Even though those types of computer architecture are non-symbolic, they're still run on discrete state machines, right? They're still run on a physical symbol system. So, I don't know. You know, anyway. Yeah. Oh, yeah. You said the same thing that I said. Yeah, Zach. Yeah. Like I could make a neural network on this computer right here, you know, and its neural network is supposed to be non-symbolic. Instead of discrete representations like 1s and 0s, we usually say that the representations for a neural network are distributed. They're kind of distributed across the whole network. But, you know, it's still running on a digital computer. So, you know, make of that what you will. So classical AI works well for some things. It works well for well-defined problems, or really anything that we can solve algorithmically, right? And this is kind of what Turing proved along with Alonzo Church. That's what makes a universal Turing machine universal, is that it can compute anything that's computable. Any procedure or problem that can be solved algorithmically is computable. And anything that's computable can be implemented on or can be implemented in a computer. Yes, that's true. Yeah, I remember, and I'm not really much of a programmer, but I messed with some neural nets back in the day in my PhD, and that was what a lot of the background was focused on. It's all linear algebra, because what's happening is that, well, we'll get to this, but the nodes in the neural network are all connected to, they're all in layers, and they're all connected to every node in the layer before and after, but not to the ones in the same node. And it's also got to do with the way that the inputs are represented to the network. I'll get to it, but yeah, basically, yeah, you're right. So classical AI works good for some stuff. It works good for like well-defined problems where we know all the rules that we have to follow, for example. Anything that can be solved algorithmically. That's why Newell and Simon were playing chess, right? Chess is a well-defined game. There are clear rules. Nothing unexpected. Well, that's not true. You can play a game of chess and some unexpected things might happen, like maybe one player will blunder, right? By the way, have you ever seen a chess player rage quit? It's hilarious. You can go and check it out. But some of these like super grand masters who play like bullet chess, you know, like chess where you have like 3 minutes or less, they play on the computer and they're just silently clicking so fast I can't even follow. And all of a sudden they'll make a blunder and just like scream and get up and run away. It's kind of funny when you see a chess player rage quit. But anyway, chess is well defined because nothing unexpected is going to happen in the sense that the pieces have rules they have to follow. And there's a goal. The goal is to checkmate the opponent's king. So you can solve chess, or rather, I should say play chess. You can play chess algorithmically, right? And computers are better than people at this now. I remember in the 1990s, IBM's Deep Blue computer was in the news. Yes, he is. Yeah, I was just going to say, Garry Kasparov, who was the he still is a chess grandmaster, but he was the world champion. He was like world chess champion for like 20 years. Like, I don't think people nowadays, okay, Magnus Carlsen, highest ELO rating ever, whatever. Yeah, sure. And Magnus is awesome, but Garry Kasparov was champion for 20 years. Like, whoa. And then he loses to a computer. I would be bitter too. And this is why Magnus doesn't play like AlphaGo or Alpha Chess or whatever it is. He doesn't play that because he knows he's going to get his ass handed to him. But it's fine. But yeah, Kasparov is still bitter about it. In the 90s, Kasparov lost a chess tournament to Deep Blue, and it was the first time that had happened, right? As Max says, computers can assign numeric values to the chess pieces to calculate material advantage. But human chess players do that too. Pawns are worth 1, bishops and knights are worth 3, rooks are worth 5, queen is 9, and of course, if the king is mated, you lose the game. So I can do that too, and I do. It's a helpful heuristic. A heuristic would be like a heuristic is like a rule of thumb, a procedure we give the computer. Like, okay, if I have a trade, am I going to be up the exchange in terms of material, right? If I trade my rook for a bishop, that's bad. I'm going to be down 2 points. But if I can take your bishop and all I lose is a pawn, well, yeah, then that's good. Well, yeah, you're right. Okay, you're right about that. It's not really a rule. Well, a rule of thumb, right? A rule of thumb, a heuristic. It's not like if we stalemate, we go and count up our material and whoever has the most material wins. No, if we stalemate, we stalemate, right? But yeah, you're right. You're right. So I understand. Yeah. So they're good for things like chess or indeed math. I mean, math or logic. Search. Probably early AI was all search, right? Search is where you have a problem space and you want to get from your start state to your solution state. In the game of chess, problem space is huge. I still don't think we've solved chess. Maybe we're getting close. I'm actually not sure. We've solved checkers. Solved tic-tac-toe. We've solved checkers. We haven't solved chess. That means we don't know every possible game that could happen. There's just too many darn games that could happen in chess. And Go, forget about it. We haven't even come close. Yeah, okay, yeah. I figured we haven't solved it. There's too many possible games, right? Too many possible games. But search, if you want to use chess as an example, to play chess, search is where the computer is trying to find the path through the problem space, the pathway through all the possible games, from the goal or from the start state to the solution state, which is checkmate. And of course, the problem space is going to change as the game unfolds, right? As soon as I make a move, maybe I play the English opening, all right? So if I remember correctly, that's c5, pawn to c5. No, c3. Yeah, ABC. No. Oh my God. I can't visualize a chessboard. Pawn to c4. Yeah. 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 Yeah, that's right. And that's why Google's alpha chess thingy, whatever it's called, that's kind of what it does. Right. And that's what heuristics are meant to do in symbolic search, is to limit the search space. But of course, as soon as I make an opening, I'm also shrinking the search space. The longer the game goes on, the smaller the search space gets, but it's still huge. Humans, of course, don't play this way. Humans use intuition and sort of like gut feeling and memory. Chess grandmasters always have really good memory, right? If you want to be good at chess, you kind of just have to have a good memory. You need good working memory so that you don't get like queen blindness. But you need a good memory because really there's so much theory that you need to know. Chess today is very theory oriented. You need to know some openings, and I'm not preaching at you like I'm some kind of expert in this. I'm just a thoroughgoing amateur chess nerd, and I'm still learning my stuff. So, but the point is that that this is the way it's like now. So, decision trees are another thing that classical AI is good for. You can give a classical AI, say, a database of stuff and a learning algorithm, and it could construct a decision tree based on past stuff. So, like bank loans. Maybe there's some bank has a database of who's qualified for a loan and who has not, but they want to automate the process. So they'll have a learning algorithm, maybe like ID3. And the learning algorithm will construct a decision tree out of all of this data. And they'll use that decision tree, the set of rules it comes up with, to make a loan wizard. Those wizards where all you have to do is answer a couple questions and it tells you whether you would qualify or not qualify for a loan. Well, those things are built using learning algorithms on big databases of information. And of course, logic. Anything formal, but especially logic. I just realized that I have this missed opportunity to talk about Shaky the robot. And Shaky the robot was probably the first autonomous robot. And its language was predicate calculus, logic, like literally what philosophers do. And what Sherdley would have to do, or not Sherdley, Shaky, what Shaky would have to do is, like go into a room and get a box and bring it into a different room, something like that. It does that by having its goal state represented in predicate calculus and then looking at the way the world is and then working out how to get from there to the goal state, all in logic. So really cool. And in the 1950s and 60s, there was a lot of optimism about this stuff. People like Herbert Newell and Alan Newell and Herbert Simon thought that we would have artificial general intelligence in 10 or 20 years. But of course, it's 2020 and this hasn't happened. And Dreyfus shows us why. This is why Dreyfus is important. He uses a sort of Heideggerian and later on a sort of Wittgensteinian approach to explain why this early optimism was maybe a bit unjustified. Now, if my computer will work. Oh, there we go. So Dreyfus argues, to quote from Dusek, following Heidegger, but also the later philosophy of Ludwig Wittgenstein, a source of most ordinary language philosophy of Britain and the USA, that the rules at the basis of thinking cannot be fully formalized or made fully explicit, right? So again, just to get back to this old chestnut, thinkers from the pre-Socratic philosophers to Plato and Aristotle, through Descartes and Kant and onward, thought of the world as out there, separate from us, right? Present to hand, as Heidegger would say. We don't really stand apart from the world in this way. We can't really stand apart and characterize everything in terms of rules and procedures, because as Heidegger pointed out, we're situated in the world in such a way that we're sort of always interacting with it. The objects of thought, entities in the world, especially when we're getting along and being, is ready to hand, not present to hand. So a lot of this is the basis for Dreyfus arguing that we can't really fully formalize rules for thinking, because our behavior is not governed the same way that like a symbolic AI is. We're embodied agents situated in a physical environment, and that environment changes over time. AIs are not built to deal with that sort of thing. They're good at solving math problems, but maybe not so good at navigating the world as self-driving cars show. And if you think self-driving cars are really smart, I have some bad news for you. Most of their knowledge about the environment is not from their sensors, it's from their human programmers, right? We give them the maps they need. They're not just out there sensing the world. You can't just drop one somewhere and expect it to drive well. Yeah, so anyway. So maybe we don't think and judge with explicit rules. And of course, a lot of that stuff comes from the continental tradition, Heidegger, and maybe not necessarily Wittgenstein, but definitely Heidegger. But there's some interesting findings from the analytic tradition that converge with what we're talking about. And I'm thinking of like the incompleteness theorem from Kurt Gödel. The incompleteness theorem says that in any formal system, there's going to be statements that you can make in the language of that system that you're never going to be able to prove. And that's just kind of the way that formal systems work. And if the human mind is like this, well, maybe there are some things that are not computable for the human mind, in which case, if we're trying to go for artificial general intelligent action, like strong AI, maybe computers, maybe symbolic AI is the wrong approach. And maybe the mind as computer analogy is the wrong way to understand our minds. As I mentioned before, like, unless you're a robot, most computers are not embodied or situated in an environment, right? Unless you're a robot. And even when we make robots like this, sometimes we have trouble getting them to do what we want them to do, right? Dusek talks briefly about Gestalt psychology here. So I'll say a little bit about that. Oh boy, we're getting close to the end. So Husserl and the other phenomenologists, Dusek says, follow the so-called Gestalt psychologists in claiming that perceptual experience is structured in terms of figure and ground relationships. A Gestalt is an organized figure or shape. So the ground is the background over which we experience the figure. One cool example, I guess, that is maybe a little shop-worn, but is the Necker cube. So you've probably seen a Necker cube. It's always, usually displayed against a white background. It's just two squares joined together, but you can kind of make it flip when you look at it. I'll share a link in the Discord in case anyone's not sure what I'm talking about. But it's one of those things whose orientation seems to change, even though the representation doesn't change, right? Or think of like one of those things that, is it a vase or is it two faces looking at one another? Or the duck rabbit, is it a duck or a rabbit, right? There's any number of these things. Gestalt is the background, and the figure is what we experience. So you have this Gestalt shift in the case of necker cubes and duck rabbits, where the ground remains the same, but what you actually perceive changes. And the ground is often not within conscious awareness, but it will structure our focal awareness. So the idea is in Gestalt psychology that experience, perception, and conscious and cognition kind of have like layers to them of figure, of ground and figure, right? But Searle kind of takes this cue from the Gestalt psychologists and says that we have in our perception and cognition these horizons. Dusek explains like this: there's the outer horizon of the indefinite distance in perception, or the indefinite iteration of some operation in cognition. There's also the inner horizon of the unfocused upon aspects of our focal objects. Kind of like, sounds to me like the inner side of the grounds, but again, I'm probably woefully underfamiliar with Gestalt psychology to explain this properly. I think the key takeaway with anything like this is to realize that cognition and perception are quite holistic, right? You know, with the environment, we're not standing apart from anything and thinking about stuff like Aristotle sitting by his lagoon thinking about what the frogs are for. What's the telos of these frogs? If I think about it, I can know. Like, no, that's not what we're doing. Says Husserl. No, we're like in the world. Or Heidegger, you know, we're being in the world. We're beings who are being in the world in a dynamic environment over time. And the way our perception and cognition works reflects that. It's not some simple input, computation, output, or sense, think, act like the computer scientists thought. It is not that simple. So yeah, as I said, this field of consciousness, our whole conscious experience, is holistic. And this is a very different conception of intelligence and reasoning than one finds, as I said, in classical AI, in the analytic tradition, or even, heck, most of philosophy going back even before Plato. There is a worry here, though, and that is that Dusek seems to me to be equivocating between consciousness here when he's talking about Husserl and Gestalt psychology and phenomenology, and reason when he's talking about the philosophical tradition. This is very important, but intelligence and consciousness are not the same. Everybody asks me, because I research the robo philosophy and stuff like that. They ask me, if we have strong AI, does that mean our robot or AI or whatever it is conscious? Well, not necessarily. Consciousness, when we talk about consciousness in philosophy, what we're talking about is usually subjective consciousness or phenomenal consciousness. You should watch Ghost in the Shell. Oh, it better be the anime. Yeah, it has to be the anime. Yeah. I didn't even see that one with Scarlett Johansson. What's the point? Why would I? Oh, that's really cool. Would a strong AI hear Laurel or Yanni? Well, if it were conscious, it would hear one of them. But is it conscious, right? See, when we talk about consciousness, and at least in philosophy, we're talking about phenomenal subjective consciousness, right? Like, what is it like? What's it like? You know, we talk about things like qualia, like the smell of coffee, that unique, private, subjective, what its likeness. These are qualia. So the smell of coffee is a quail. A beautiful horse is a quail. What else do I have? I don't really have that much cool stuff around here. I guess the sound of a guitar. That's out of tune. That the sound is a quail, or a quale. Quail. No, it's quale. It's not quail, it's quale. And plural is qualia, right? So that's what we're interested in. You could have intelligence without that. right? You could be like a philosophical zombie. And if you're interested in any of this and you have the time, I am teaching a class on consciousness right now. I don't suggest you go and watch everything. That would be ridiculous. But if you're interested in some of this and you want to follow up on something, I probably have a video about it. You might want to check it out. So, so I don't think that Dusek is aware of this. Well, that's uncharitable. I hope he's aware of this, but there is a difference between intelligence and consciousness, and a strong AI need not even be conscious, right? And you could have conscious creatures that are not that intelligent. Like, okay, so I'm pretty sure that a goldfish is conscious to a limited extent, right? But it's not very smart. My dog is smarter and probably conscious. I'm pretty sure she's conscious. Pretty sure she's not a zombie or a beast machine. You know, what are we, Descartes? No. So yeah, that you can have intelligence and consciousness. They are not mutually exclusive. They are actually separable. So what does Dreyfus say here? Well, thought and intention assume a body, not the mechanical body, as described by physics and chemistry, but a lived body in the sense of Maurice Merleau-Ponty, a follower and developer of the ideas of the later Husserl. Yeah, we are embodied. Again, check out, if you want to know more of this, this is a really great book, Mindware by Andy Clark, philosopher of mind at the University of Edinburgh, I believe. And he published a very famous paper together with David Chalmers, called The Extended Mind, which is about the extended mind hypothesis, which is very cool. The idea that cognition doesn't just happen in the head. Cognition is something that's distributed throughout the brain, body, and world. And you can see here the similarity of this to the idea of the lived body, the body as experienced from the inside, like me, like right here. Like, yeah, my body is a machine in the Cartesian sense. Like, sure, this is like a mechanism. Remember, Descartes had like a sort of mind-body dualism. If you've taken philosophy class, you'll know that. But René Descartes, the father of rationalism in the European tradition, he's got this sort of mind-body dualism, where the mind is unextended thinking substance, basically the soul, but the body is a machine made by God. And animals are just machines. They don't have souls. The beast machines, he called them. The lived body is very different from this. Dusek explains it as follows. He says, the lived body is experienced from within as an intrinsic part of our orientation to the world and objects. It contrasts with the body studied by biology and medicine from without as an external object confronting us. So again, very different from the mind-body dualism of Descartes. And a big part of Dreyfus's critique of classical AI is that it just doesn't treat intelligence the right way. We should be thinking more like the phenomenologists, less like Descartes. And again, this is explored in areas of research like embodied cognition, the extended mind hypothesis, and some of these may help to solve to fail to account for. Now, it's time to go, but we're not quite done. So I think I'm going to save this neural network stuff for next time. So let's just stop sharing the screen. So, yeah, for next time, we'll finish these off, and then we're going to start chapter 6, which is technological determinism. And then going forward, we will lecture on little whatever is chosen in the poll that's on Discord. So remember, I put an announcement up about this. There is a poll on Discord where you can go and vote on chapters 7 through 12. Vote for the one you want to hear the most about. I will lecture on the most popular ones. I think right now, well, I can let you know actually. Right now, autonomous technology is the most popular, followed by anti-technology, and then followed by women, feminism, and technology. If that's where it stays, I'm happy to teach on those three things. I think those would all be very interesting. But not many people have voted so far. So if you haven't voted, go on Discord and vote in that poll. Max, will we talk about in the loop and out of the loop AI systems? I'm actually not sure what you mean by that. I can talk about, when we're talking about neural networks, I could talk a little bit about recurrent neural networks and deep networks and convoluted networks. I can talk about those things, but I'm not quite sure what you're referring to there. Maybe I'll look it up and then learn about it so I can talk about it. I don't know.
If I could just like quickly say it.
Yeah.
Okay, in the loop system is when the human is the one that gives the authorization in reaction or like on a case-by-case basis for the AI machine. So like the example is like an automatic gun, like a sentry turret. So an in the loop system is when like the sentry turret is like looking at, you know, the field and then sees someone, and then the human gives the authorization to shoot. They effectively press the trigger, whereas out of the loop is when they give the pre-authorization to shoot when they see something. So they're not really, you don't have the control to make the decision to do the action or not.
Gotcha. Okay. I think that, yeah, sorry. Sorry, go ahead.
I was just saying it seems kind of similar to when you're talking about like using technology as like a tool versus like having it be out of your hands. And that's like something that's decided like when you make the AI itself.
Right.
It's not like a thing that's like random. That's like a thing that you would either program in, or it's like a consideration of like to what extent it's a human operated tool.
Yeah. And I think we should probably circle back to this when we talk about autonomous technology, but also if anyone is thinking of writing their paper on whether technology is neutral, I mentioned this to a student in an email the other day, but this kind of strikes me as a similar discussion to one surrounding nuclear technology in a paper by Langdon Winner called Do Artifacts Have Politics? If anyone's writing about the neutrality of technology in their paper, I seriously encourage you to check this paper out. You may find it very helpful. But anyway, Max, it just sounds similar to that, what you're saying here, being in the loop, out of the loop. Even building a feature like that into the technology makes the technology more or less neutral, depending on how we built it, right? Anyway, Langdon Winner's probably the person you want to read, not me. But anyway, that's all for today. So I'll see you all on Thursday. Oh yeah, someone had a question. Yes, go ahead. About the term proposal structure. Yeah, go ahead. Oh, thanks, Max. That's helpful. So yeah, I guess I'll leave it there, and I'll stick around to answer Stefan's question. But if you want to take off, then I'll see you next time. All right. Yep. Bye, everyone. Yeah, see you all Thursday. All right. So, Stefan, as it is, I currently have the area of interest thesis and a slight abstract about the plan of attack. Is it fine for the rest to be more or less a direct approach? So actual arguments? Yeah, I mean, you could tell me like, okay, so I'm going to be doing an adjudicative thing or a positive or a negative argument. And then you can kind of give me, you don't have to explain everything, but you can kind of give me the main premises and conclusion of your argument and just say a little bit about what kinds of evidence you'll use to support it. So yeah, you want to treat it like an abstract, basically. That's a good way of doing it. So yeah, I would say that's fine for the proposal. For the essay, save some of the arguments for the actual essay, right? But yeah, you want to have a sort of, okay, I'm going to start by talking about this. I'll survey this literature, and then I'll start my argument, and I'll present the following, sort of premises toward the end of supporting this conclusion here. You know, that's what I would do. So does that answer your question? Okay, perfect. And of course, if you still find you're sort of spinning your wheels a little bit, send me an email or hit me up on Discord, and maybe we could meet up. We could have like a Zoom meeting or something and hash some stuff out. And that goes for everybody, not just Stefan, obviously. If anybody's stuck and you're like, let me know and I'll try and get those wheels turning. We can do it together. Sometimes it just helps to have another mind to bounce ideas off of, right? So anyway, that's all for now. Thanks, everyone. I'll see you Thursday. Okay, bye.